Have you ever looked at one of those incredibly detailed 3D models, of a building, or maybe a huge map for a new road, all made by a drone, and just thought, how accurate is that? Like, really, can we actually trust these things, especially when, they're being used for critical infrastructure? Welcome to the deep dive. Our mission today is to kind of peel back the layers, get into the core ideas that define accuracy in UAV mapping. We're diving into this really comprehensive document. It's called UAV Mapping Accuracy with RMS.pdf. It's by Atiz Ahmad Hakimi bin Matnoor from University Tun Hussein on Malaysia, UTHM. It covers the theory, the workflow, quality reports, specifically looking at JKR projects, that's Malaysia's Public Works Department. So yeah, our goal is basically to give you a shortcut to understanding all the complex stuff behind drone maps.
And it's so important to understand this stuff. Really, it is. Because without getting these concepts, a drone map is, well, it's just a pretty picture, isn't it?
Yeah.
But once you grasp this, you see how those images become genuinely reliable data. Data that engineers, that designers can actually bang on with confidence. It's about trusting the data itself.
Okay, right. Let's get into the nuts and bolts then. So UAV mapping. Basically taking aerial photos and turning them into 2D and 3D maps. Simple enough on the surface. But what really dictates the accuracy, the source points to a few key things. Ground control points, GCPs, checkpoint CPs. Then there's RTK, real-time kinematic, and PPK, post-process kinematic. And of course, other factors too, like the IMU, projection, triangulation, and this thing called the point cloud. Lots to unpack there.
Yeah, and one of the first things, something that often gets a bit confused, is the difference between GCPs and CPs. It's actually crucial. Think of GCPs as like anchors. Real-world anchors. They're points on the ground you've measured really, really precisely. Their job is to tie the drone model, the whole data set, to a known coordinate system. This gives you what we call internal accuracy. Basically, how well does the software fit the model to those points you fed it?
Okay, anchors. Got it. So what about CPs then? Checkpoints.
Right, CPs. They are also measured points on the ground. But here's the key difference, the kicker, really. You don't use them when you're calibrating the model. You hold them back. Their whole purpose is verification. An independent check. They test the absolute accuracy of the entire model after it's built. So when you see an RMS value for CPs and RMS CP, that's your proof. That's the number telling you the true real-world accuracy of the point cloud, and therefore the ortho photos, the DSMs, the DTMs that come from it. It's like the audit.
Oh, okay. That makes sense. So RMS root mean square error. The source calls it the quantitative indicator of spatial accuracy. And it sounds like it's, well, fundamental. This is the number that tells you if your drone map is just nice to look at or if it's actually solid enough for engineering, for design work. It measures the average error, right, between the real coordinates on the ground and the coordinates in your model. Smaller RMS means better accuracy.
Exactly. Lower RMS, less error, higher accuracy.
Yeah.
Simple as that. And if we look a bit deeper, the relationship between the RMS for the GCPs and the RMS for the CPs, that's where you get the real insight. RMS GCP tells you about internal consistency, like how well did the software manage to mathematically fit the model to the GCPs you gave it. But RMS CP, that's what tells you the actual external accuracy. It's the validation against points the model hasn't seen before during processing. So the big takeaway here is GCPs tie the model down during calibration, CPs validate its overall accuracy afterwards, and that RMS CP figure, that's generally the more reliable indicator of the map's true accuracy out in the real world. Remember, the GCPs are used in the process. CPs test the results of the process.
That distinction is really clear now. And the document, it gets very specific about what RMS values are needed depending on the job, using those JKR references. Like for general road design, maybe some infrastructure planning, you're looking at maybe plus or minus 5 to 10 centimeters horizontally, the XY plane, and maybe 10 to 15 centimeters vertically, the Z axis.
That's pretty typical for general work.
But then if you're dealing with something like slopes or detailed earthwork calculations, it gets tighter. Suddenly it's plus or minus 3 to 5 centimeters for XY and 5 to 8 centimeters for Z, and the vertical accuracy, the Z, becomes much more critical there, right?
Absolutely. For volumes and stability, that Z value is paramount.
And then structures, bridges, buildings, even tighter, plus or minus 1 to 3 centimeters horizontally and 2 to 5 centimeters vertically. That's incredibly precise. And for cadastre, defining property boundaries, legally binding stuff, it's less than plus or minus 2 centimeter XY and less than 3 centimeters Z.
Now,
Accuracy really isn't just one number. It depends heavily on the application.
Exactly. You tailor the method to meet the required precision. Which brings us to how you achieve that kind of precision, especially consistently. That's where things like RTK and PPK come in.
Right, the kinematic techniques.
Yeah. So RTK, real-time kinematic. Picture this. Your drone is flying, and it's constantly talking to a base station on the ground. That base station knows its position extremely accurately. It sends correction data to the drone in real time as it flies, so the drone records highly accurate positions for each photo it takes.
Live corrections. Okay. And PPK.
PPK, post-process kinematic. It's a bit different. The drone still records its raw GNSS data, and so does a base station, but they don't need that constant communication link during the flight. You collect all the data, drone logs, base station logs, and then after the flight, back in the office, you process it all together. This calculates the highly accurate positions retrospectively.
Ah, so you get the accuracy without needing that continuous radio link.
Precisely. It offers more flexibility, maybe in areas with tricky radio signals or for longer flights.
Yeah.
Both RTK and PPK dramatically improve the accuracy of the camera positions, which often means you could use fewer GCPs on the ground. Not necessarily zero, but fewer.
Makes sense. And you mentioned the IMU earlier, the inertial measurement unit. How does that fit in?
The IMU.
Yeah.
It's sort of the unsung hero inside the drone. It's constantly measuring the drone's orientation, its pitch, roll, and yaw, like how it's tilted or rotated in the air as it takes each picture.
Yeah.
That orientation data is absolutely critical for the software later on, for things like triangulation, figuring out where points are in 3D, and for georeferencing the whole project correctly.
And projection and scale. The source mentions that flight altitude gives an initial scale, but it might not be perfect?
That's right. Flying higher or lower changes the scale of the photos, obviously, and the software uses that as a starting point. But without accurate ground control, like GCPs or the highly accurate camera positions from RTK PPK, that initial scale drive just from altitude, and the camera might have some drift or error. It won't be, perfectly locked to the real-world scale and coordinate system. You need those external references, GCPs, RTK, or PPK, to really guarantee that the final map or model is dimensionally accurate.
Got it. So all these measurements, the GCPs, the RTK PPK, the IMU data, they all feed into creating this point cloud, which the source says is the foundation. What exactly is a point cloud?
Yeah, it really is the foundation. Think of it as just a massive collection of individual points, millions, sometimes billions of them. Each point has an X, a Y, and a Z coordinate, placing it precisely in 3D space. Together, all these points represent the surface of whatever the drone flew over the ground, buildings, trees, everything.
How are they actually formed? The source mentions photogrammetry and LiDAR.
Mostly photogrammetry in the context we're discussing, which means it's derived from those overlapping photos we talked about, combined with the GPS and IMU data from the drone. LiDAR is different, it uses laser pulses, but photogrammetry uses images. The software identifies common features in overlapping photos and calculates their 3D position. And each point in the cloud can also store other information, like color values, or RGB, taken from the photos, or maybe intensity if it's from LiDAR. So you end up with this incredibly rich, detailed 3D data set made of just points.
Millions of points. Okay. Can you walk us through how you get from photos to that cloud? Step by step, maybe?
Sure. It's quite an elegant process, actually. First, the drone flies its mission, capturing images with lots of overlap, typically 70, maybe 80%, sometimes more. High overlap is key.
Okay, overlap. Check.
Then, back in the software, step one is feature extraction. The software scans each image and finds unique, distinctive points like the corner of a building, a specific rock, things it can recognize again.
It finds unique pixels.
Essentially, yes.
Yeah.
Patterns of pixels. Then comes image matching. It looks for those same unique features across multiple overlapping images. It says, this point in image 1 is the same as that point in image 2 and image 3.
Right.
Once it has matched thousands of these points across many images, it uses photogrammetric principles, the geometry of the camera positions and orientations, to perform reconstruction. This calculates the 3D coordinates, X, Y, Z, for each matched point. And the result of calculating all those 3D coordinates, that is your point cloud, a dense collection of 3D points representing the scene.
And the core principle behind calculating those 3D coordinates, that's triangulation, right?
Exactly. Triangulation is the geometric heart of it. It's a simple idea, really. If you see the same object or point from two or more different known locations, the camera positions, you can figure out where that object is in 3D space. Imagine lines extending from each camera position towards the point, where those lines intersect. That's your calculated 3D coordinate for the point.
Okay. Now, the source also mentions interpolation. How is that different from triangulation?
Good question. They work together, but they do different things.
Yeah.
Triangulation, as we said, generates the actual 3D points in the point cloud based on the photos. It creates the raw data points.
Right.
Interpolation comes after you have the point cloud. It's the process of filling in the spaces between those measured or calculated points to create a continuous surface, like a digital surface model, DSM, or a 3D mesh.
So it's like connecting the dots?
Kind of, yeah. It estimates the elevation or surface value in locations where you don't have an actual point, based on the values of the points nearby. So triangulation makes the points, interpolation makes the smooth surface from the points, triangulation is the basis, interpolation builds on it.
Okay, that clarifies it. So let's try and trace that path again. From the drone's camera to the final models. The drone captures images, which are just 2D pixels initially, right? Like U and V coordinates on the sensor.
Correct, just flat images.
Then this process, structure from motion or SFM, finds those tie points the features seen in multiple images.
Yes, it identifies and matches them.
Triangulation then converts those 2D pixel coordinates into real-world 3D coordinates X, Y, Z.
Exactly, using the known camera positions and orientations.
And doing that for thousands, millions of points creates the raw point cloud.
That's the one.
And from that point cloud, we then generate the other products like the DSM, the DEM digital elevation model, maybe a textured 3D mesh.
Precisely. The point cloud is the fundamental 3D dataset from which all those other useful deliverables are derived.
Now, how does the quality of the camera itself and how high you fly impact the detail in that point cloud? The source talks about resolution, GSD, and density.
Right, they're all interconnected and really important for accuracy and detail. Camera resolution is your starting point. More megapixels generally means the potential for more detail. A 25 megapixel camera can capture finer details than a 20 megapixel one, assuming similar sensor quality.
Okay, more pixels, more potential detail. What about GSD? Ground sampling distance.
GSD is crucial. It tells you how much ground area is covered by a single pixel in your photograph. The formula is basically sensor pixel size times flight altitude divided by the camera's focal length.
Okay.
The key thing to remember is a lower GSD is better. A GSD of, say, 2 centimeters means each pixel represents a 2 by 2 centimeter square on the ground. A GSD of 5 centimeters means each pixel covers a 5 by 5 centimeter square. So lower GSD equals higher resolution on the ground, more detail.
Lower GSD, sharper image. Got it. And how does that connect to point cloud density?
Directly. If you have a lower GSD, it means more pixels are covering the same area on the ground across your overlapping photos. This gives the software more information, more potential tie points to find and match. More matched points, calculated via triangulation, leads to a denser point cloud, more points per square meter. A denser cloud generally means a more detailed and accurate representation of the surface.
Ah, I see the chain reaction.
Yeah. So basically, high camera resolution allows for potentially low GSD by flying lower or using a longer focal length, and low GSD leads to high point cloud density, which supports high accuracy models. They all work together.
Okay, this is all tying together nicely. Now, the source uses a Pix4D quality report as an example to show how this stuff is presented in practice. It says these reports usually show the RMS for GCPs, that internal accuracy we talked about, and ideally, the RMS for CPs, the absolute accuracy check.
Correct. A good quality report should show both.
But it highlights the specific JKR slope project, where they actually measured CPs in the field, but well, they weren't included in the final report shown in the document, so only the RMS GCP was visible.
Yeah, that's a really interesting point the source makes.
And the implication seems clear. If those CPs had been included, the report would be, as the source puts it, audit ready. It would provide that independent, verifiable proof of the actual accuracy achieved.
Exactly. It highlights the difference between showing how well the model fit the control points used to make it, RMS GCP, versus showing how accurately the final model represents the real ground, RMS CP. You really need the latter for full confidence, especially for engineering acceptance.
It really drives home why understanding what should be in these reports is so important.
Absolutely. So if we boil it all down, the core message, I think, is that GCPs remain absolutely critical. They are fundamental for ensuring your UAV products, orthos, DSMs, DTMs, models, are genuinely accurate and suitable for serious engineering work. Yes, RTK and PPK are fantastic technologies. They significantly improve accuracy. They reduce the number of GCPs you might need, but they don't usually eliminate the need for GCPs entirely, especially for the highest accuracy requirements or as validation checks. They provide the essential tie to the ground truth.
Right. And that independent check, the CPs and the RMS analysis derived from them, that's non-negotiable if you need to prove the accuracy of what you've delivered. It's really that combination, isn't it? Smart use of GCPs, independent validation with CPs, careful analysis of the RMS values, Only then can you confidently say, yes, this drone data meets the spec, whether it's JPR guidelines or any other rigorous standard.
Couldn't agree more. It's the whole package that delivers trustworthy results.
So, thinking about all this, how might this deeper dive into UAV accuracy change how you, our listener, look at things? When you see that next drone map for a big infrastructure plan, or maybe even just for checking property lines, what critical questions might you ask now? What level of accuracy proof would you want to see? Something to think about.